What is up, everybody? Mr. Hissner here, and today we're going to be looking at congruence and the properties of congruence. And what we will see is that they're pretty similar to properties of equality, and the idea of congruence is different than equality in that figures are congruent. Remember, figures are not numbers. Numbers are equal. Numbers can use algebra too, but whenever we're dealing with figures like line segments, angles, triangles, those things are not equal. Those things are congruent. So we're going to look at those properties of congruence. And here we have, so just as a reminder, these were our properties of equality. And yeah, so, those are what we've been working with. These can only be used when there is an equal sign. Whenever we have a congruent sign, we have different properties. So the reflexive property of congruence is very similar. It's just, okay, so if we have segment AB, we will know that the reflexive property is AB looking at itself in the mirror. So very similar. It's just now it's a segment. The symmetric property, so if we have AB is congruent to CD, then we have CD will be congruent to AB. So again, that same idea of symmetry. If we were to fold this in half, it would kind of fold up onto itself. So that is the symmetric property of congruence. And finally, we have the transitive property. And again, this was a property that we saw with algebra, with the equality as well. So if AB is congruent to CD, and CD is congruent to EF, then if A is equal to B and B is equal to C, then A is equal to C, then AB is congruent to EF. So we just kind of skip that CD there. So again, you should be taking notes on this if I haven't said that already, because we're going to be doing a note submission for these. So these are our properties of congruence. And just remember that not only do we have these different properties of congruence, but we also have definitions. Now, the definition of congruence is biconditional. So this is an if and only if statement, or you could say that this would be a conditional and a converse, right? So let's look at the conditional statement. So two segments biconditional first. Segments are congruent if and only if they have the same measure. So conditionally, if AB is congruent to CD, then AB is equal to CD. So the measures are the same, right? And then so this is if P then Q, and this will be if Q then P. So we'll have if the measures are the same, then the two segments are congruent. So this is the biconditional statement up here in white. This is the conditional statement, and then this would be the converse. And when both the converse and the conditional statement are true, it is a biconditional statement. So just know that these two are kind of the way that we see these. If the segments are congruent, then their measures are equal. If the measures are equal, then they are congruent. That is the definition of congruence. And we have one more, excuse me, and it's the midpoint. Now, a lot of you probably remember the midpoint. Midpoint of segment divides it into two equal parts, and those two parts are congruent. So if M is the midpoint of AB, then AM is equal to MB. So again, if it looks like this, A, B, and M, then A, B, and M, then these two segments are congruent, thus they have equal length. And now we have one more piece to the puzzle, and that is if we have three collinear points. So if we have 3 points that are all on the same line, that means we can add their measures. We can add the one piece, so we can take the left pocket piece plus the right pocket piece, BC, and set it equal to the whole thing, AC. So again, that's the idea that we have two things in our pockets, excuse me, and we can add them together. So hopefully you all will be, submitting your notes from this, and in the next lesson or the next video, we will be looking at how we can apply this knowledge. Thanks for watching.